Hi, everybody. Welcome back to another lecture of artificial intelligence. So now today we start a new chapter. We're talking about probabilistic methods. And in the first lecture, we're talking about probabilistic methods for static environment with no actions, and that can be realized with Bayesian networks. Right, so first we talk generally how we humans act under uncertainty, or how we could, in principle, develop a technical system acting under uncertainty. And then we will quickly realize that we will need probability theory. Most of you had probability theory in their previous studies, but we are going to recap some basics in case somebody doesn't know these. And then we are going to apply those to create Bayesian networks, which will mostly be networks that utilize conditional independence of random variables. And then similarly to inference and logics, we will have a section on inference and Bayesian networks where we compute certain probabilities. And in the end, we will look at some approximate inference methods, because in contrast to logics, as we have studied before, with probabilities, you can easily approximate them. Of course, with logics, you can just say it's true or false, so there is no approximation, but with probabilities, of course, you can approximate the values. And the content of this lecture is also covered in the AI book by the section Quantifying Uncertainty and Probabilistic Reasoning. As always, let's begin with the learning outcomes. So the first part is just basics of probability theory. So you should understand the concept of probability space, random variable, expectation, and conditional probability. And based on conditional probability, you can easily apply Bayes' rule, which also many of you already know. And you can determine whether two random variables are independent or conditionally independent. So independence is quite well known. Conditional independence maybe is new to probably more than half of the students of you. And based on conditionally independent variables, we can then create a Bayesian network, and you can apply inference by enumeration and inference by variable elimination for a given Bayesian network. And since this is computationally expensive, there are two tricks. So one is to apply variable ordering and variable relevance to simplify inference computations. Similarly to constraint satisfaction problems, we can also save a lot of computation time by choosing the right order of how we evaluate certain variables. Just a side note, so like this week, a former student contacted me because he gives an internal seminar in his company about, it's also an AI company about, and it's the internal seminar will be about constraint satisfaction problems, and he wanted to have the latest slide. So this shows you also that these types of methods that you learn here are very much in need in all the companies around the world. Also, of course, the topic regarding Bayesian network. Okay, and then finally, as I mentioned, because we work with probabilities, we can approximate the probability values using Monte Carlo methods. And there we will look into direct sampling, rejection sampling, and likelihood weighing. Okay, so just to start, why are we doing this? The problem when you use logics is that you need exact knowledge about the world. And as you know, not only because of fake news, but of many other effects. For instance, you have unreliable sensors in a robot. You do not always have exact or complete information. Nevertheless, we have to design systems that act rationally given the uncertain information. So you have to factor in the degree of uncertainty. And let's say you have a solution that might be very good, but you have very little information about the environment. Then another solution where you have a lot of knowledge about the environment, but it's not in the best case as good, then you would maybe choose the one which is better in most cases and not only in the best case. So as an example, let's look at the plan A90, which is an abbreviation for leaving for the airport 90 minutes before the flight. So which is a rather good choice if you're flying, let's say, from Munich and you want to reach the airport in 90 minutes. That's usually no problem. Of course, you also, I mean, the 90 minutes is before the flight. So if it's not the transcontinental flight, then 90 minutes is a good time. However, this might not be always successful, because it could be that the bus is not coming, the subway has broken down, you're running out of gas if you go with your own vehicle, and so on, or you're involved in an accident, and then of course this plan doesn't work. But this also holds for the A180 or the A900 plan. The only way is, like, if you would live at the airport, then it would be safe. Even then, maybe you could break your leg at the airport or whatever. There are also, like this, you know this, right? There's this movie about this person who lived at the airport for many years because they were trapped because of visa issues. So, but yeah, this is a little bit off topic, but yeah, you would never be 100% sure. So what you have to do is you have to find a solution that on average gives you the best benefits. So we need to minimize the expected cost to the goal. Okay, so let's look at another example. We can look at the dentist example again. I mean, we are using this example because it's also in the book, so that there is some, yeah, so that there's some continuity. However, of course, it's a little bit of a nasty example. So if you use logics, you could write the statement, toothache implies cavity. However, there could be other reasons why you have a toothache, right? So you could have a gum problem or other issues. So then you would have to write toothache implies cavity or gum problem or abscess or whatever. Then you're like, okay, this list can go on forever, or it would be a very long list. So let's turn this around, right? So we could say, okay, cavity implies toothache. However, this is also not true in all cases, because there are people who have a cavity but no toothache. So you see the problem already if you would, for some cases, use logics. Of course, if you look at the digital circuit example that we looked at for first order logic modeling, there you didn't have this problem, because the circuit is the circuit, there is no uncertainty. There's many problems with no uncertainty, but if you have a medical problem or other problems, then you have to deal with that. So the problem with logics is sometimes you don't have enough data because of laziness reasons, but laziness is maybe a little bit of a wrong word. It's just like it's not worth collecting all the data. So this here is written under laziness, but it's not always laziness. So what other problems do we have if you use, for some applications, standard logics? And again, it always depends on the application. Sometimes logics is the best way to go forward. Sometimes probabilistic methods are the best way. Maybe if you want to type in the chat, then I can see your thoughts. Okay, there's not much going on. I'm just testing whether my chat works. Okay, yeah, it works. Okay, good. So then, yeah, so other problems are theoretical ignorance. The governing laws are not known, like in medicine. So of course, the dream of many doctors is that maybe if you have your genetic data, that you can have the perfect treatment just for you, because they know exactly how a medication will work in your body, because all the working principles of your body would be somehow known to a certain degree, of course. But this is not the case. That's why in the pharmaceutical industry and in other industries, they always work with probabilities. Also, like, of course, with corona vaccination, you only get certain probabilities of how well it works. If you would exactly know how the virus would work in our body, we might be able to find a vaccine that works in 100% of all cases. And there's also practical ignorance. Our word description is just not accurate enough. Like, we know in principle, for instance, how what the physics of weather is, but it's such a connected and complicated and large system that the weather prediction, of course, for 1 week in the future is not really working. I mean, I know there are these weather forecasts for 2 or 3 months in the future, but yeah, it's a little bit tricky, I would say. Okay. Yes, so somebody wrote, we cannot know all the causes. Sorry, I've seen this too late. Yeah, but exactly, that's the governing laws are unknown case. Okay, so we will then work with a degree of belief. So we believe certain facts only up to a certain degree. And one option to express the degree of belief is, of course, to use probabilities. And as an example, if an agent is convinced of a sensor reading by 0.9, that means that 9 out of 10 times this would be correct. And of course, probabilities subsume the uncertainty caused by the lack of knowledge. And of course, for some aspects, if you know exactly what's going on, then these facts will have probability of 1, and all other things will be in between, of course. Yeah, as I mentioned at the beginning of this lecture, when we will use Bayesian networks in this lecture, and this will be for static environments without actions. And then we will kind of fill up these 4 sectors over the next lectures. So if you have a dynamic environment and no actions, then we will use hidden Markov models. This is also very important, especially for prediction. So you just predict what the world will be like, but you don't take any actions. And then after that, we will look into decision networks, where you can act, but you can only act in an episodic, no, in an episodic environment. So only for one snapshot. And if this also is in a dynamic environment where things change over time, then we will, and you have actions, then we will look into and use a Markov decision processes. Okay. So now comes a short section on recapitulating basics of probability theory. So first of all, we have to start with the sample space, which is nothing else than all outcomes of a system. So if you toss a coin, then you can produce heads or tails. If you look at the traffic light, it can be red, yellow, or green, things like that. So these will be denoted, the set of possible outcomes will be denoted by omega, and one element will be denoted by a small omega. Also, because of Corona, now we get a good repetition of the Greek alphabet. I'm sure we will quite soon be at omega if you look at the variance. Okay, so then the event space is nothing else than all possible combinations of outcomes. So it's just a power set of the sample space. So if you look at the tossing coin example, it could be nothing, heads, tails, or heads and tails. Of course, there are things among the power set that are completely impossible, but this will be resolved by just giving it a probability of 0. And of course, you could say, okay, if you throw a coin or toss a coin, you can only have heads or tails. But if you're very lucky or unlucky, depends on how you see it, it could be that it lands on the side. So if you don't have a perfect coin, so none of these outcomes would also be an outcome, or it disappears in the sewage system or something like that. And heads and tails then would have a probability of 0, because that's really not possible. At least I couldn't come up with an example for that. Okay, so then the probability space consists of the sample space omega, the event space f, so the power set of omega, and a function that assigns a probability to each event of the event space, such that if you have, so first of all the probabilities have to be greater or equal to 0. And then if you have disjoint or mutually exclusive events, that means that if you sum up the probabilities of these events, you get also the probability of the joint event. And the probabilities, of course, across the whole event space have to, or across the whole sample space have to sum up to 1. Okay, so for the coin tossing example here, we decided to have an ideal coin. So that nothing happens has probability 0, and that heads appears as 1 minus the probability of tails. So usually the probability of tails is 50%, so it's 50% for heads as well. And then this sums up to 1. Okay, so for many, yes, so there will be some tweetback questions later on. Somebody asked about tweetback, but we'll show you the link soon. But this is just a repetition of things that most people already know, and we'll be finished quite soon with that. So for many operations, like computing the expected value, you need numbers instead of things like heads or tails, or red, green, and yellow. And that's why we need to introduce random variables, which do nothing else than mapping the sample space to some other set D. And in our case, or in most cases, it's a number set. So we call X a random variable. And in the tossing coin example, we could assign 1 to heads and 2 to tails. So now, because we work with numbers, we can compute the expectation of a random variable, where we just weigh the outcome of a random variable with its probability and sum those up. And this is basically just a definition. So it's basically the average value that you obtain. And if you have a dice with numbers from 1 to 6, then on average you would throw a 3.5. It's also interesting how old dice are already. So I was in Pompeii this year, and I of course did it because due to the pandemic there was not much going on there, and there you could already see dice from more than 2,000 years ago. It's quite interesting. Okay. So now let's talk about multidimensional random variables. So you have not just one random variable X, but another one Y. Of course, the name is unimportant, but of course they can have different values. So this means the event that the value of the random variable X is X, and the value of the random variable Y is Y, and that returns the probability of this joint event. So now we can use marginalization. So let's say all the outcomes are exclusive or mutually exclusive in this case. What we can do, we can sum up over all outcomes of the random variable Y. And by that, we can obtain the probability that the random variable X has a certain value. So this is, of course, possible because if these events are mutually exclusive, then you sum up over all of them and just get the probability of one random variable. So when you throw the dice, for instance, or when you throw 2 dice, what you can do, you want to know the probability that the first dice has a value of 3, and then you sum up over all probabilities, or over all probabilities of all values of the other dice. No, what is the singular of dice? I forgot. Die, yes, it's a die. And yes, and by doing that, we sum 6 times. We sum up 1 over 36 6 times and become 1 over 6, which of course is as expected the value for throwing the value 3 with the first die. Okay, the next thing is conditional probability, and this is defined as follows: the probability that the random variable X has the value X, given that we already know that the random variable Y has the value Y, is as follows. It's the joint probability divided by the probability that Y has the value Y, so that the random variable Y has the value Y. And of course, as you already see, this is always a little bit silly. We always say the random variable Y has the value Y. Later on, we will not use this notation anymore, but this is, of course, mathematically the cleanest way of introducing probabilities. But we will use a simpler notation later on, which is more compact. Okay, so as an example, and the numbers are guessed here, we have football example. So we're looking at who is a fan of FC Bayern München. So there are two groups, people who live in Munich and people who live somewhere else in Germany. And then among these groups, some are fans of FC Bayern München, others are not fans of FC Bayern München. And these are the joint probabilities. So 0.006 is the probability that you live in Munich and are a fan of FC Bayern München, for instance. And now what we are interested in is what is the probability that you're a fan of FC Bayern München given that you live in Munich, which is probably higher than if you live somewhere else in Germany. Of course, there could be some small villages where there's a lot of fans and the conditional probability is higher, but in Munich it should already be quite high. So, so what we first have to do, we have to compute the probability that you live in Munich. And of course, that's just by adding up the two probabilities here, 0.06 plus 0.07, and then you obtain 0.013. This here we use, of course, marginalization, that we summed up over all the possibilities, and the possibilities that you're a fan or not a fan. And then now we can use this formula here where we look at the joint probability. So the joint probability of living in Munich and being a fan of FC Bayern München is 0.006, and that we divide by 0.013, and then we get a probability of roughly 46%. Okay. Good. And now what we can do, we can use the definition of conditional probability to obtain Bayes' rule. So essentially, what we are doing first is we are rearranging this equation that we have here. Sorry. So if you look at this equation, we multiply this equation on both sides with the probability of y equals y. And then we have on the, sorry again, then here this cancels, and we just have the joint probability. On the left side, we have the conditional probability times the probability that y has the value y. And this is this formula now. And now what we can do, we can insert this into, again, a conditional probability, but now the conditional probability, for that conditional probability, we have changed cause and effect. So now y is on the left side and x is on the right side. So here it was different, x is on the left and y is on the right. And if we insert this joint probability now in here, then we get this, we get Bayes' rule. And essentially what Bayes' rule is doing is it changes cause and effect. So here we have, so the cause is x and effect is y. And here we have the other way around. So we have here, we have the effect is x and the cause is y. And just by multiplying this with the probability of y and dividing it by the probability of x, you can then change this order. There's also another way of writing Bayes' rule. Sometimes you don't exactly have access to the probability that x has the value, that the random variable x has the value x. So what you can do, you can take the joint probability, use marginalization, and then obtain obtain this formula here. And this can be inserted again. So sorry, one more thing. Yeah, so what we have done is we have taken this formula in one, and we're summing over all values of y. That returns, because of marginalization, returns the probability of x. And this here is then this part multiplied or summed over all y, and this is then this right side. And this, the probability of x being x can now be inserted here, and this will be replaced with this formula so that we obtain this formula here. I mean, I can just use my pen for those who couldn't follow. So essentially we take this formula and then we sum both sides with all values of y. And then as shown here, the left part is the same as probability of x. And this is then inserted here. And we are saying, and we know that this is equals this. So essentially, we're inserting this value here. And this then, by this, we have this final solution here. It's just a way, I mean, usually this first formula suffices. The second formula is not used that much. Okay. Now let's look at an example. So a few years ago, this was always a nice example, but now I think Susanne is teaching this in discrete probability theory, this example, this Monty Hall problem. So I think at least half of you know this problem already, right? Maybe we can do a quick feedback question. Who already knows this Monty Hall problem? So I think then A would be yes and B would be no. Yeah, somebody wrote it's discussed in DWT. Okay, yes. So I'm waiting in the meantime for the outcome. Okay, so in Germany, the corresponding TV show was called Georg's Ganze with Jörg Träger, but nobody knows it anymore. I used to watch it sometimes. It was just it's just a show where you can switch your brain off. It's quite silly, but especially it was because I knew as a student already that you always have to switch the door. Sorry, now that sorry, I shouldn't have said that. But then it was always funny to watch the people thinking back and forth what they should do. Okay, so what's the problem for those who don't know? So this is not the entire game show. There's several games, but one game is that you have 3 doors or gates, and behind one gate is a prize like a car or something like that. Behind one is nothing, and behind another one, behind 2 others is nothing, like a goat, for instance. In Germany, it was called the Zonk is behind one of the doors. And let's say you pick door number 1, and then the host, who knows what's behind the doors, opens another door, and in this case, door 3, which is a goat, and then asks you, okay, do you want to pick door number 2? So should you change or not? And sorry, I already said what is the best solution, so we can skip this tweetback, but there will be other tweetbacks later on. And now we can compute what's the best solution based on Bayes' rule. Okay, so we have to introduce 2 random variables. First one is x, and if x equals xi, this corresponds to the prices behind door I. Okay, and then we have another random variable y, and if the value is yj, this corresponds to the host has opened door j. Okay. And we assume that the game show has no bias, so the probabilities that the prices behind any of the doors is always the same. It's 1/3. And now comes the interesting part. So now we can discuss some conditional probabilities. So the first one is, okay, the host has opened door 3, given that you have chosen door number 1. No, sorry, given that the price is behind door number 1, and what you need to know is we have chosen we picked door 1. So without loss of generality, we pick door 1. If you pick another door, it doesn't matter. So we pick door number 1. The price is behind door number 1, and the show host set open door number 3. So what would be the conditional probability for that? You can just type it in the chat. Yes, 1/2. So he could have opened door number 2 or number 3. Both would have been fine. Okay, let's look at the probability. Okay, the host opens door number 3, given that the price is behind door number 2. So what's that probability? Again, please. And we have picked door number 1. Yeah, the probability is 1. Here's no other choice. We picked door number 1. Of course, he will not open our door. And he knows, okay, the price is behind 2, so he will not open the door of the price. Then we say, yeah, I will take this door. So then only door number 2 remains. And then the last one is, okay, the host opens door number 3, given that the price is behind door number 3. And that, of course, is 0, unless the showmaster makes a mistake. But we assume he's a very experienced showmaster and doesn't make any mistake. So now this is the interesting part, and the rest is just applying Bayes' rule. So if you now insert this information into Bayes' rule, so we want to know what is the probability that we should change the door, so that we should choose door number 2 instead of number 1, given that the showmaster has opened door number 3. And this is the formula for Bayes' rule that we just use here. Then we insert all the conditional probabilities that we have collected, and then you see that the probability is 2/3. And this is twice as high as the original probability. So if you switch the door, your chance of winning has doubled. And yes, so the reason is just that when the door master, the showmaster, it's also the door master, opens a door, he reveals some information to you that you can encode using this conditional probabilities. And based on that, because the showmaster only makes certain decisions in certain circumstances, because you can infer this, you can make a better choice. So again, in this lecture, we're not only talking about Bayesian networks, we won't take any actions. But in lecture 11, when we take actions, we can also tell you later on in the lecture how much value the information has, how much value the information has when the showmaster opens one door. You can even calculate that, but this comes later in the lecture. Okay. Okay, I should go back to full screen. Okay, so then we're almost done with our repetition of probability or probability theory basics. So from the definition of conditional probability, we have this formula that the joint probability is the conditional probability times the probability of y. And so now what we can do is we can say, okay, let's assume that the probability of x has nothing to do with what value y has. And that means that x is independent. So the random variable x is independent from the random variable y. And then if you replace, again, I can use my pen. So now if you replace this here with this, so that you replace it with the probability of x, then you obtain this formula that the joint probability is the same as the probabilities of this individual random variables multiplied with each other. Again, we can look at our FC Bayern München example. We know from the previous computation what is the probability that you live in Munich, and then we can also compute the probability that you're a fan of FC Bayern München. So you just have to add this number with this number, And now we could multiply the probabilities of the individual random variables. And this multiplication is a different value compared to the joint probability that is written in the table. And of course, because this formula doesn't hold, it means that being a fan of FC Bayern München depends on where you live. The probability depends on where you live. And that, of course, is obvious. Okay. Okay, so now we have a first serious feedback question. I can ask this question because I studied mechanical engineering. It's okay for me to ask this. So the idea is that there's the saying that mechanical students, it's very likely that mechanical students have a Karohemd. There's also some other saying about this, which I'm not going to say because the lecture is recorded. And yeah, so you can now choose between three values for the conditional probability. And the conditional probability is that what's the probability that wait a second, Y2 is that you do not have a Karohemd if you study mechanical engineering.
Okay, so about 60% chooses C, and then around 30% chooses A.
Mm-hmm. Okay, yeah, C is correct. So so what do we need? So we need the joint probability of Y2 and X1, which is 0.02. And the probability of just X1 is 0.08 plus 0.02, which is 0.1. And 0.02 divided by 0.1 is 0.02 divided by 0.1 is 0.2, which is 20%. So you need a little, if you're not good at calculating this in your head, you need a pen and paper to compute this. Okay. Okay, the next question is, are X and Y independent? So again, can you set in the, you can say yes or no question, right, in feedback. So this would be yes or no question.
Yeah. So now it's 80% chooses no.
Yeah, that's correct. So how can we see this? I mean, of course, you can say, yeah, that's obvious from my own experience, but yes, mathematically, so we know the probability of Y given X, like the probability of having not a Karohemd given that you're studying mechanical engineering is 0.2, and the probability of having no Karohemd, wait a second, this is 0.82, which is much higher. So you just add these two numbers. And that's why the probability of just Y2 is much higher than the joint probability. It's the conditional probability given that you're studying mechanical engineering, and that's why it's not independent. Okay, so this independence is rather straightforward. So what's a little bit more complicated is conditional independence. So the random variable X is conditionally independent of Y given Z if you have probability of X given Y and Z is the same as the probability of X given Z. So we will look into practical examples later on. Here you just see how this can also be written. Maybe again use my pen to explain this a little bit better. So we start with this conditional probability here. And then we just use the definition of conditional probabilities. So we can use the joint probability of X, Y, and Z divided by the probability of Z. So this step is just the definition. And then we use the chain rule. So you can see if you multiply these two probabilities, we get the probability, and now I use already the short form of y given, no, sorry, of, this is the joint probability of y and z. And this can then be multiplied. Here again, you see that the condition resembles the probability here. And if you multiply these, then you get, as a result, the joint probability of x, y, and z. Okay, so that's basically what you had here, the joint probability. Okay, and then what happens is that this probability and this probability cancels, and then you get this final result here. So if, oh, okay, sorry. Yeah, so if this probability equals this probability, you also know that you have conditional independence. But as with the Bayesian formulas for Bayesian for Bayes rule, the first formula here is much easier to understand. It's just here so that you, if you see it in another form, that you're not shocked. Okay, now that you've always used this notation, the random variable has a certain value, and that then is an event. This is, of course, mathematically very clean. However, it's very cumbersome to always write this. So now we will introduce some simplifications for the notation. So instead of writing the probability that the weather is sunny has 60%, we will write p sunny 0.6 by assuming that the value sunny is not used by any other random variable. So let's say you have another random variable which describes the mood of a person, and one value would be, oh, he has a sunny mood today. Then you cannot use the simplification because you don't know whether the value, whether p sunny now belongs to the mood or to the weather. But we assume that this is there is no other use of sunny. Then we will use for Boolean random variables another simplification. So instead of saying, okay, a random variable is true, we will just use the name of the random variable, but without capitalization. And if it's false, we use again the name of the random variable, but also not without capitalization, and put this negation symbol in front of this name. So that is good because then you don't have this problem that you need values to be unique. But of course, this trick only works if you have Boolean values. And the last one is, let's say weather has 4 possible values, and you fix the order of the values. You say the first value is always sunny, the second is rain, the third is cloudy, and the fourth is snow. Then you can always write this as a vector where you just put in all the values, and then you already know, okay, this means this here, where the sunny has this probability, rain has this probability, and so on. Okay. The next thing which is nice is that if you work with Boolean variables, you can always use normalization and don't have to, and this is another possibility to compute conditional probabilities. So this is the last thing probably we're going to do today. And then I hand over to the exercise. So if you want to compute the conditional probability that you have a cavity given toothache, and cavity here is capitalized, meaning we want to know the probability that it's true, and we want to know the probability that it's false. So what we are going to do is we compute, instead of the conditional probability, we will compute the joint probability and normalizes by this value alpha. Because toothache, if you have this, so just a second, I use the pen again. So this again, by definition, is nothing else than the joint probability divided by the probability of toothache. And dividing by probabilities can be realized by normal or multiplication with alpha, which normalizes the values. So we have now given this table, and there we have all the joint probabilities of toothache, catch, and cavity, but we don't, we don't care about catch here. By the way, catch is the steel needle with which the dentist goes over the T's and T's whether it catches in a cavity. But what we then do is we are going to sum over the hidden variables. In this case, it's catch. And so we use this joint probability, cavity toothache catch and cavity toothache not catch, to obtain the joint probability of cavity and toothache. Insert the numbers from the table, add the numbers, and then we use normalization. So we have 12% and 8% here. Of course, this doesn't sum up to 100%. So we find an alpha such that we raise both numbers equally, such that in the end they sum up to 1. So this is what the normalization does. So now we computed this conditional probability without computing a conditional probability, but by using normalization. And this trick is used later on several times. That's why it's here introduced. And the general idea is always we compute the distribution on the query variable. So the query variable, what we want to know is the probability of cavity, by fixing evidence variables. So the evidence here is toothache. This is given because it's a conditional probability, and summing over hidden variables here, the catch. These are not appearing in our request here or in our formula, and these we have to sum up in the background to obtain this probability that we want in the end. Okay, so then I'll stop here. There was just one last question. Why do we add the probability of not cavity? So the thing is, not cavity. Yes, so the thing is, cavity is capitalized here. So capital means, if you go back, that we look at all the values, and if it's Boolean variable, we look at the value of true and false. So this probability, the first element is for true and the second element is for false. And here they're saying the first is for true and the second is for false, while toothache and catch are fixed. All the variables that are capitalized are random variables, they're not fixed, and the other ones are fixed outcomes. Okay, good. So now I really have to stop, otherwise you have not enough time for the exercise. So then I wish you a nice weekend and see you next week. And one more thing, like as some of you also, I entered yesterday the Zoom and then realized that we have these academicos. So I was in Zoom for a few seconds and I've seen that there were a few other people, but I think you all realized that we had no lecture yesterday. Okay, so then, yeah, bye.
Okay. Hello, let me just prepare everything. That should be that. Yes, that seems to work. Okay. And I think I am good to go now. I think there are some questions in the chat. No. Do we have a break? Yeah, perhaps let's say 2 minutes until 50. That way I can make sure that everything is working. Is my microphone still working? Can you also see me?
Yes.
Perfect. Yeah, then let's make a break until 50 and then we'll continue. Okay, so hello everybody. We are going to continue today with the logic exercise. And so the first exercise will be about the knights and knaves. Just one thing before I forget. I have a little bit of trouble like separating on my screen like the Zoom chat and the tweetback chat. So I would appreciate if you could put everything on the tweetback and nothing on the Zoom chats in case I'm missing something. But yeah, so let's continue with the knights and knaves exercise. So basically, this exercise is based on this relatively long text that I'm not going to read because it's too long. But basically, the idea is just there are knights who always say the truth and knaves who always lie when they say something. And the first part of the exercise is how can we formalize that thing? So for example, if you have the sentence A says that B is a knight, how do we put this in propositional logic? Well, sometimes like here, it helps to sort of see what the different cases can be, right? So for example, if we just focus on the variable A for the moment, there are basically two cases. Whoops. So either A is a knight or A is a knave. And now, just for this exercise, what we're going to do is we're going to associate the fact that somebody is a knight to the fact that that certain variable, so to speak, is true. And knave, we're going to associate it with false. So if we say that A is true, then it means that A is a knight. And if we say that A is false, it means that A is a knave. So if A is a knight, meaning that A is true, then A is saying always the truth, right? And if A says that B is a knight, then it also means that B is a knight, because yeah, A always says the truth. Whoops. So in that case, B is a knight as well. Yeah. And if A is a knave, so A is false in that case, then for the exact same reason, but in the other way, so A is always saying something which is wrong. And since A said that B is a knight, well, that has to be wrong, and therefore B has to be a knave. Okay, and this you can also do in the other direction. Also works in the other direction. And so what we get is that A is a knight if and only if B is a knight. And how do we write this in propositional logic? Well, it's just like this, right? So basically, you can say if A is a knight, then B is a knight. If A is a knave, B is a knave, and also vice versa. And that's just basically what the equivalence does. So I think somebody is not happy with the way I say knight. Yeah, doing my best. But yeah, I hope you understand what I mean here. Okay, then let's go one step further. And this time we have some person, P, right? This can be A, B, or C. And that person says something, which is a remark, right? And we have to formalize now the thing that the person P says something. Oh, it's the way my handwriting looks. Yeah, my handwriting is extremely terrible, but yeah, again, I hope it's good enough. So about the sentence P says a certain remark. So here the idea is still the same, right? I mean, we can use the same arguments that we had before, that we have two cases. Whoops. Case 1 and case 2. So if P is a knight, let me write it correctly here. And if P is a knave. And again, if P is a knight, well, it always says something. He always says that there's something that is true, and therefore the remark itself has to be true as well. And the same if P is a knave, then this means that just the remark is false. And so for exactly the same reason, basically, that we had before, this can just be formalized as P equivalent to remark. Right? So again, if P is true, meaning that if P is a knight, then remark is true. And if remark is true, then P is true as well. And yeah, same for wrong. I see a question, can 431 be the disjunction? So you mean something like this, right? So that cannot be the case because, how should I say? If you have the sentence A says that B is a knight, right? You know that the sentence has been said, right? So the sentence itself, this thing here, is true, okay? But if you look at what happens if you have that A is a knave, okay? If A is a knave, this thing on the right side is always false, right? Because it's just an and. And therefore, it cannot be a good representation of this sentence above, because you know that this sentence has been said, so you know that this sentence is true. But if you put A is a knave, which may happen, then this thing would be false. So therefore, this thing cannot be a good representation of the sentence above. Oops. So, okay. Then let's continue. So now we have to model the following two sentences. Let's start with the first one. So B replies, right? We saw before how we have to do when somebody says something, right? So it's basically just an equivalence, and then on the left side, the person that says that thing. So in that case, it's B. And what does he say? What does he say? Let me put some brackets here. So he says that A said that, okay, so again, somebody is saying something. So we put a little equivalence here. And who said it? Well, it's A. And A said that he is a knave. And I saw in the Moodle forum like a few hours ago that actually somebody might have misunderstood this little here. He applies to A in this case. Yeah, I think I'm going to correct this in the exercise sheets because this is an easy mistake to do. But basically, so he said A says that A is a knave, that he himself is a knave, and therefore he says that not A is true. So that A is false, meaning that A is a knave. Okay, so that's the first sentence. The second sentence is relatively similar. So C says, okay, so somebody says something. Who is the person that says something? It's C. And he says, don't believe B, he is lying. So he is saying that B is lying, meaning he is saying that B is a knave. So he is saying that not B is true. Okay, and that's how you formalize those two sentences. And now we're going to use those two sentences to determine what is B and what is C. And what we are allowed to use are those two little logical equivalences that we're going to use in a minute, and also the following inference rule. So let's start. So we had in the first sentence this thing. Right? And so for this red part here, we can actually directly use this logical equivalence to just say, okay, this is the same as just false. And so we have B equivalent to false. And then we just use the second rule here. Let me put it in blue to say that, so yeah, logical equivalence to say that not, this is equivalent to not B. And so we know that this sentence up here has been said. So this sentence is true, so to speak. And therefore we have determined that this is just the same as saying that not B has to be true. And see, if not B is true, well, it means that B has to be false, and therefore that B is a knave. Now, let me just do it for the second sentence as well, and then I will answer the questions. So for the second sentence, we had C equivalent to not B. And what we're going to do here is that we're going to use this thing as well. So not B, right? And now I put a little line here, and we are going to use now this inference rule. And this inference rule tells us that we can infer C. So in other words, that C has to be true. In other words, that C is a knight. So in case you are asking the question, what can we infer about A? I think A is a little bit more complicated. I'm not even sure if we can infer anything about it, because at least not with those two sentences, because we don't have something about A except this thing here on the top, but we know that this is false because B is a knave. So yeah, I don't think we can determine A here. Okay, so let me answer some questions in 4, 3, 3, 1. Okay. Is that the one you mean? No, I think you mean this one. Yes. Can you explain again why it is A equivalent to not A? Can it be A not A equivalent to true? So it cannot be A equivalent to true, right? Because A is not saying, how should I say? A is not saying something which is always true, right? He is saying that he himself is not a knight. Okay, sorry. Yes, he himself is not a knight. So he is saying that he himself is not true. Okay. I think I might have mixed up here something, but yeah, the idea is just he is specifically saying that he is a knave, meaning that he is not a knight, meaning that he is not true. Okay, and so the not he is a knave means that this he is saying that he is true. Yeah, so, sorry, I realized that might have confused a little bit more than what it might have brought, but A equivalent to true would not have worked, because in that case it would have just meant that he himself had said that he is always right. And that's not what he said. He is saying that he is always wrong, so to speak. Okay. 433, can we also write B equivalent to A equivalent to false? Okay, so that's the other question. So no, you cannot write here A equivalent to false, because again, he's not saying that, how should I say? He's not saying something which is always false. He is saying something about the state of himself, right? He is saying that he himself is a knave. And that's why false would not be enough, so to speak. So it would be too general, and it would not apply to just A, so to speak. Okay. We know that A did not say I am a knave, right? However, maybe A said that I am a chicken, so it is not really helpful. Exactly. So you cannot really determine what A actually said or what A actually is. What if A says for himself that he is a knight? Should it then be A equivalent to A? Yes. If it was something like A said that he is a knight, then it would have been something like this. And then it could also be that A, in fact, is a knave, but this relation would still work, right? This is just a formalization of what this sentence is. It does not necessarily tell you anything about A, right? It just says that, okay, this person said this. Because you can also see that this equivalence is actually still true if A is a knave, right? So if A is false, this equivalence is also true. Okay, I think I have, if he is a knave, shouldn't he lie about he being a knave? Yes, wait. Yes, exactly. If he is a knave, he would lie about saying that he is a knave. That is correct. But okay, I think I have answered all the questions that I see, at least. If you have any others, then don't hesitate to ask. Okay, then let's turn to the last exercise for this exercise sheet. So here we are going to show that Superman does not exist, right? And we are given relatively long text. Now, again, I'm not going to read it. I'm going to jump right into the exercise. But basically, we are also given some logical sentences, and those I'm going to read really quickly because they are important. So we have A for Superman is able to prevent evil. W for Superman is willing to prevent evil. I for he is impotent. M for he is malevolent. P, Superman prevents evil, and Superman exists. This is just to remember a little bit what letter refers to what. Okay, so we now want to prove that Superman does not exist. How do we do this? Well, first of all, we have to formalize the sentences that we have in this text. Oops. Here we go. So the first thing that you notice is here you have some ifs, right? So if, then he would do so. And always when you see an if, there should be something in your mind that's like an alarm clock that tells you, there's an if here, so I need an implication. Okay, and that's what we're going to do here. So if Superman were able, so able was A, and so literally and willing, so W, to prevent evil, he would do so. So he would prevent evil. So if that were true, then he would prevent evil. Then we do the same here for this if. So if Superman were unable to prevent evil, so if he were not able, now again, we need an implication, he would be impotent. So that's an I here. Okay, I will just finish those sentences and then I'll answer all the questions. Then, if he were unwilling to prevent evil, so again, if he were unwilling, so he was not willing, then he would be malevolent. Okay, then Superman does not prevent evil, so he does not prevent it. There's no if here, so we don't need an implication or something like this. If Superman exists, so if he exists, he is neither impotent, so he is not impotent, and he is not malevolent. Okay, and that's how you formalize those sentences. Now let me go through some of the questions. So there's one about knave. In this world, no one can ever say, I am a knave. Yes, I think that is correct. Yeah, indeed. Isn't this just the theodicy problem, but substituted with God with Superman? What do you guys have with this problem? Like literally, somebody else like last year also asked that question in a mail. I have no idea where you interpret this, but okay, if you want. I mean, yeah, it was a long story last year, but yeah, I'm not going to deal with that. Why we use I instead of not P? So if he does not prevent evil, right? I think I was, he is impotent. Yeah, okay, I can see what you mean here, but the thing is, impotent is really when we use the word impotent, so to speak. Shouldn't we have S for Superman too? Yeah, perhaps, but yeah, that's how we just defined it in the exercise sheet. Does Superman exist? Probably not. I haven't seen him, so I can't tell him. I can't tell. Anyway, okay. So now that we have formalized our sentences, we want to show that Superman does not exist. How do we do this? Well, we want to do this with resolution, because that's sort of the easiest way to do this in this case. So what is resolution? You have seen it in the lecture. That basically the idea is you have a certain knowledge base. So the knowledge base is all the sentences that we have deduced before. And then you add the negation of your goal, right? So if you want to show that he does not exist, then you add to this knowledge base the sentence he exists, right? And then you have to transform everything into a conjunctive normal form. And you use the resolution rule. We're going to see later how this works exactly. And you basically do this until you end up with an empty clause. And when you end up with an empty clause, this means that you have shown that this thing is unsatisfiable. So no matter what you do, this thing is always going to be wrong. And therefore, if you take the non-negated goal, so your actual goal, then this will always be true, assuming that your knowledge base is true as well. Okay, and that's how you show that a certain sentence is entailed by a knowledge base. But we're going to see in more detail now how this works. Let me just go through the questions. How do we decide when to use equivalence and when to use implication? So basically an implication is everywhere where you have this if then, right? So the left side implies the right side, but not necessarily vice versa. And the equivalence is vice versa. So the left side implies the right side, and the right side does imply the left side. So that was, for example, the thing with the knight. That's why I said that you can also do it in the other way if you wish. Why Superman does not prevent evil? It's given in the exercise like this. So yeah, I mean, we needed to do the logic exercise. So yeah, let's just define it that way. Okay, so I said something about a resolution rule. What exactly is that? So this is basically the statement that you have in the lecture, but to put it in a slightly easier way and more than sufficient way for our purpose. Basically, what you have, if you have two clauses which look like this, then you can sort of combine them by deleting this blue part, and you just end up with a, A or C. Okay, so basically if you have a variable and not that variable, you can just delete them. Okay, either way. One thing that we need to do before we actually use the resolution algorithm is transform everything into conjunctive normal form. And the conjunctive normal form is basically just some clauses which are separated by ands, and in those clauses you have only ors. Okay. Okay, I'll look at the questions later. So for example, this right here would not be a conjunctive normal form, because yes, you can see that as a clause. Okay, that's a clause, that's a clause, that's a clause. But okay, here you have an or which is not in a clause, right? And here it's the same. You have an and which is in a clause, and that's not allowed for conjunctive normal forms. On the other hand, here you have, okay, a clause and that and clause, clause, and okay, here we have a new thing, and in that thing we only have ors. So this is fine. This is a conjunctive normal form. Somebody asked, please go back to the last slide, 31. I'm not sure what I can say more about this. I mean, you'll see it in action in a minute. So yeah. Okay, so the first step is that we need to convert everything to conjunctive normal forms, right? So I'm going to do this a little bit fast now because it's not necessarily extremely interesting. Basically, it's the same mechanisms that we used in problem 2, where you basically transform everything into an easier form, right? So let me go back here. Here we go. So again, you just eliminate the implication. You use the De Morgan rule. You use the distribution rule if you need it. But at the end of the day, you get this, not A or not W. Whoops. or P. This will be A or I. This will be W or M. This will just stay the same. And this will be a little bit more complicated. Not E or not M. Okay. So let me just analyze a little bit what we ended up with. So here, this first part, we just have ORs, right? And therefore, this is going to be one clause. The same is true for here. So we have only an OR. So this is just a clause. This is also just a clause. This is, of course, just a clause. Like a single element can also be a clause. And here it's a little bit more complicated. We have one clause here and another one here, separated by this and. Okay. Yes. And then we have the negation of our goal. So if our goal is to show that he does not exist, then that means that we need the negation of our goal, which would just be he exists, right? Okay. And then what you do, you just write them all in a line, and I'll do the resolution graph in a minute. Let me just check the questions. In the exam, do we need to annotate the rule we are using while doing equivalency conversion? It depends. It depends on the exercise. Yes, there's probably going to be some easy exercises where you don't need to show it, but yeah. You are very fast, please slow down. Okay, yeah, sorry. I mean, again, this slide, I'm not going to go into detail because it's the same thing that you did in the second exercise. But yeah, I'll try to slow down. If there's something particular that you have problems with, I can perhaps repeat it as well. Okay. So now that we have all the clauses lined up, let's combine them using the resolution rule. Wait, let me just wait for one question. Slide 32, can you explain again why this example is no? So this thing here is not a conjunctive normal form because, I mean, there are two reasons. First, you have an or, which is not in a clause, right? So basically the ors have to be somewhere in brackets. And you have an and here, which is in some brackets, and that is not allowed. Then why do we need to prove that the knowledge base entails alpha to show that alpha is true? I mean, that's basically what this entailment tells you, right? If you know that your knowledge base is true, then you can say that alpha is true as well, right? So you're sort of relying on the knowledge base being true to show that alpha is true. Okay. So finally, let's go to the resolution graph. And so we're going to start here on the left side. So we have here an A and a not A. So we can cancel them and just write W or P or I. Okay. So we combine those two. Now we can do the same again with this clause and this clause now, because we have here a W and a not W. So what remains is the P or I or M. Then we can do again the same thing with this not P and this P. What remains is I or M. Okay. And how did I want to do this? Yeah, let's do it that way. Okay. There's typically several different possibilities that you can choose, but yeah, I'm just going to choose that one that I wrote here. So here we cancel the I because we have it here and here. So what remains is M or not E. Oops. And now this is perhaps the part where it's a little bit tricky. So on the one side, we need to combine those two, right? Because you have an E, a not E and an E, so they cancel. And you are ending up with not M. And now the thing is, you can use a clause several times, right? So you can also see that here, this E here, you can cancel it with that one. So you can combine those two things. Oops, let me make a little bit of a tunnel here. Here we go. And you end up with M. And finally, we have our M here and our not M here. And you can combine those two and you end up with the empty clause. And so the empty clause just means, okay, great. We have shown that our knowledge base of all the sentences we had about Superman, that this entails not E. Okay, and that's how you do a resolution graph. Now, a few remarks about this, and then I'll go to questions. So first, there are many students, for good reasons, that ask the question, okay, it's great that you showed this, fantastic, it works, great, but how are we doing this in the exam? Are we sure to find this thing? Is it easy to find this resolution graph, or what? Is it easy to see what clauses you have to combine with each other? And so the answer is, it depends. It depends a lot on the knowledge base. In the exam, there's going to be examples which are easy to solve, but in the general case, yes, you would need to check for each clause, like all the different combinations, which might take a long time. And in fact, there's a good reason for that. This problem is actually NP hard. So sometimes you can see it very easily, and sometimes you can't. Yeah, this is an example where, like, I put it already in such a way that it was easy to combine, but in general, it can be much more difficult than that. Another thing that I want to emphasize here, in the exam, there were some students, I have no clue where they learned it that way, but who decided they were just smarter than everyone else, and they decided not to put the goal here, right? And what you can do is, if you do that, you can actually say every single one of those sentences, like for example, this M, right? If you end up with M, you can actually go a little bit faster and say, yeah, actually this knowledge base entails not M, right? Because if I had, wait, is that correct? No, sorry, it entails M. Whoops, where is my eraser? It entails M because if I add the negation of my goal, and that negation of my goal is not M, right? Then I get the empty clause directly. And so they just drew this entire graph without adding the negation of the goal to it. Now the thing is, that might seem like a smart idea in the start, but in inference graphs like the one I just drew, you will actually get an error because you would not have thought about combining it here with two clauses at the same time, right? So this thing and this thing you might have missed. And there's a lot of, I mean a lot, then there's a couple of people that did it in the pseudo-smart way and lost points because they didn't complete this graph and it was wrong at the end of the day. So please, 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 please always do it like this. Don't try to be smart here. Always put the goal and the negation of the goal to the inference graph, even if you think it's going to be faster in the smart way, let's say, it might lead to errors. Okay, so let me answer the many questions that have popped up. So during problem 443, yes, should we depth first, breadth first? As I said, there's not really any good strategy that I can give you here. There are some strategies that can make it a little bit faster, but I mean, this is just the satisfiability problem, sort of. And yeah, it's typically you just try a few things, and when you have exhausted all the possibilities and you see, okay, I still didn't end up with the empty clause, then it typically means that the knowledge base does not entail the sentence. But yeah, in the worst case, you have to check every possibility, and there's not really a smart way to decide which two clauses to combine. So yeah. We can also combine M or not M or not E and not E or not M to get not E. Right, exactly. Yes, there's many possibilities how you can actually get to this empty clause. I just put this one because, yeah, it looks kind of nice with this thing here, but yeah. Okay, can we do M and not E with M and not E? Wait, you mean or? I'm not sure what you mean here. M and not E. Yeah, you might need to re-ask that question because I'm not sure what you mean. I don't have any ands here, so yeah. Why could we use the last E double? Yeah, you can use everything as many times as you wish. I really like how you explain. Oh, thank you. I hope it wasn't too fast this time. So yeah, can we argue that? Oh dear. Yeah, this is a little bit too long. Yeah, perhaps I'll go to it afterwards after I answer the other questions. I thought I've learned that one can only use a clause once. No, okay. No, so no, this is not what what we discussed in. I think I know what you mean. So in the lecture, it's a bit. Can I make a new slide? Yes, I can make a new slide. So what you probably mean is, at some point in the lecture, there was something like, what was it? A or B or yeah, let's make it easy. It was something like this, right? And what we said in the lecture is that, sure, you can use the resolution rule only once, okay? So for example, if you use the resolution rule here, you're not allowed to cancel both variables at the same time. So it's either A or B that you can cancel. And that, for example, if I cancel B here, right? Then I end up with A or not A. And this would not be the same as just the empty clause, right? Where I cancel both A and B at the same time. And so, yeah, this would have a completely different value. This would always be true. And if a clause becomes always true, then it's kind of useless because you cannot combine it with anything else afterwards. So, yeah, I think you might have mistaken it with that thing. But yeah, a clause in itself, you can combine as many times as you wish. You can just only use the resolution rule with one variable at the same time. Why do we add? Why do we have to add the negation of the goal? I mean, the dumb answer would just be that's how the algorithm works, right? But the intuition behind it is it's sort of like a proof by contradiction, right? So you assume something and you show that this assumption can in no way be true, and therefore the negation has to be true. So that's sort of the intuition behind it. The resolution algorithm is nothing but a proof by contradiction. But when we combine M with not M, we end up with not E. I mean, no, like if we combine this thing with this thing, then like the two cancel and there's nothing left. It's just the empty clause. Please let the logic programming exercise be about Santa Clauses. Oh dear. Oh dear, dear. I'm happy that I'm not the only one that thought about this joke. But yeah, anyway, what we have to negate in the infinite graph again to get the correct result. So the only thing that you have to negate is the goal, right? So if you want to show that Superman does not exist, then you have to add to the graph that it exists. So the negation of your goal. Is the size of this resolution usual for an exam? No, not at all. I would say for an exam, it would stop more or less, very big more or less about here, right? More or less 4 clauses, perhaps 5, something like this. Does not E or not M with M or not E end up with not E? No, so if you have something like not E or not M and M or not E, then again, it's the same thing Yeah. Okay, it's a bit different, but it's the same here. So you can only cancel one thing, and the only thing that you can cancel here is actually this thing. And so it becomes not E or not E, and this does indeed simplify to not E. Yes, that's actually a good question. Yeah. Why can't we combine the always true clause with the other? So you sort of have to do it that way. So if you have something, if you have two clauses, right? Let me actually write it in another way. So you have one clause one, right? So a clause, yeah, okay. Perhaps I'll write it differently again. Like for example, A or B, and you have another clause like not B or not C, right? Then you always have to imagine that this thing is actually just that. Okay, and so if you have something like true and another clause, let's say again not B or not C, right? Then you can imagine, okay, there's an, oops, I don't know what I did here. What did I do? Okay. So you put an and here and the brackets here, right? And so this sort of becomes irrelevant because yeah, you can't tell anything about the entire sentence. You just say, okay, I don't have to care about this thing. I just need to check if this is true or not to know if this entire sentence is true or not. Okay. What does adding, I know we are a little bit out of time, but yeah, let me answer the last remaining questions. What does adding something to the knowledge base mean in our logical notation? Is it just knowledge base in conjunction with a sentence? Yes, that is correct. You just add an and then whatever you want to add to the knowledge base. Without intending to sound braggadocious, the exercises are pretty easy. Is the exam on the same level? At least for the logic exercise, yes. More or less. Yeah, for this lecture, there are a lot of people coming from a lot of different horizons. So for some, it's going to be a little bit easier, for some a little bit harder, but yeah. Will we do any more exercises or only questions? Now it's only questions, I think, because we're on out of time. But when we combine M with not M, we end up with not E. What? What is if we don't want to use it twice? I'm not sure what you mean. I mean, we just have to end up with the empty clause. It doesn't matter how you end up with the empty clause. You can also draw the algorithm in a completely different way. But yeah, as long as you end up with the empty clause, you're good to go. Right side, you used E twice. Yeah, I know. Like here to, I mean, once I used it to get it here, right? And another time I used to get this thing, right? Because of this not E. So yeah, I mean, you can use it as many times as you wish. Okay, let me check the Zoom questions. I hope this will not take too much while. Yes. If there's only empty clause left, then it's not satisfiable. It's even stronger. It's completely unsatisfiable. Sorry, I just repeated what you said. Yeah, you are correct. And then the last question, is there another way? Yes, there's actually another way to draw this diagram, but yeah, not going to do it. You can do it yourself. I think it's rather at the end here. I think you can combine the E with this clause and then you do something like a little bit different, but yeah. Okay. I think that should cover it. So sorry for being a little bit over time now, but yeah, next time we will start with first order logic. Okay, I think we can stop the recording.